Newton's law of gravitation says that two point masses, m1 and m2, separated at a distance d, will exert one force on the other. This is what's known as an attractive force. So m1 will exert an attractive force on m2, pulling m2 towards m1. m2 will exert an attractive force on m1, pulling m1 towards m2. The magnitude of the force, the directions are equal and opposite, but the magnitudes are equal to each other, and they are equal to the product of the two masses divided by the distance separating them squared. It's what's known as an inverse square law. The constant of proportionality is g. This is the universal gravitational constant. So I know we've been using little g for 9.8 meters per second in class, and I usually use easy numbers and set that equal to 10. But this is the universal gravitational constant. 6.67 times 10 to the minus 11 is what it is. And it has units that make this whole combination of units be newtons. And so if you think about it, that means it has to be newtons, meters squared, kilogram to the minus 2. All right, so a couple different points on this, and then I'll give you an example and make a third point. First of all, this law satisfies Newton number 2. The magnitudes of m1 and m2, magnitude of the forces of m1 and m2 is the same as the magnitude of the force of m2 on m1, and the directions are equal and opposite, and they act along the line joining the two bodies. That's point number 2. The forces act along the line between the two masses. Okay, a third point is that for spherically symmetric masses, and I'll explain what that is in a second. To find the attraction between spherically symmetric masses, what one can do with this law, the gravitational law, is to assume that all the mass is concentrated at the center. So what do I mean by spherically symmetric? Well, spherically symmetric means imagine an onion, a perfectly spherical onion, and onions are built in shells. And if each particular shell of the onion is uniform, then spherical symmetry obtains. And the Earth is, to a pretty good approximation, is spherically symmetric. It's denser in the middle and less dense towards the surface. If you've had some geology, you know this fact. The Earth, the center of the Earth, interestingly, is under very high pressure, and it's liquid. We can tell that from the way earthquake waves go through the center of the Earth. There's only one kind that goes through. The kind that is longitudinal will go through, but the transverse earthquake waves will not. So we know from experimental data, we also know theoretically that that's true. And so although the density towards the center of the Earth is high, it's like an onion. If you take a particular shell of the Earth, think onion shells here, a shell centered on the radius on the center of the Earth will be, to a pretty good approximation, uniform. All right, so to give you an example here of number 3, let's say you had the Earth and a mass m 1,000 kilometers above the Earth. And so what I'm going to do here is, let's assume that this is a 100 kilogram person. So we would like to calculate the force that the Earth exerts on this mass, and then from Newton number 2 we can compute what the acceleration is, simply by taking the force that the Earth exerts on little m and then dividing by little m. We get the acceleration that little m experiences. Okay, so since the Earth is spherically symmetric, I can assume that all the mass of the Earth is located at the center of the Earth. And so the distance that I use when I compute the force is then not the distance that m is above the surface of the Earth. It's the distance that m is from the center of the Earth. And so that total distance is going to be the radius of the Earth, 6,400 kilometers. And then I'm taking m to be 1,000 kilometers above the surface of the Earth. And so that would mean that the Newtonian gravitational law would give me g, 6.67 times 10 to the minus 11. I'm doing this on two lines here, times the mass of the Earth, 6 times 10 to the 24th kgs, times the mass of the object, 10 to the 2 kgs, divided by 60. So we have to use kilometers to get the units right. So converting kilometers to meters, you have to use meters to get the units right. Converting kilometers to meters, the radius of the Earth, 6,400 kilometers, converts to 6.4 times 10 to the 6 meters, plus 10 to the 6 meters. And so this denominator represents the distance from the center of the Earth all the way up to m squared. So if you do the numbers on this, the force acting on m by the Earth is 731 newtons. And therefore, if I take the force acting on the Earth and I divide by the 100 kgs, I get the acceleration radially inward that m experiences, and that's just 7.31 meters per second per second. It's radially inward, and you notice that it's less than 9.8 meters per second per second. And so saying that the acceleration of gravity is constant is really just an approximation. Close to the center of the Earth, it is 9.8 meters per second per second. If you go, as I've said in class, to the top of Mount Rainier, so if you, just to greatly exaggerate things, if you went to the top of Mount Rainier, so here's Mount Rainier right here, you're further away from the center of the Earth, and the force is going to be less than if you had been at the surface, and since the force is less, the acceleration will be less. And so I want to talk about that in the next YouTube, the connection between little g and big G.